Warren, we need the microphone. Yo, stop. Okay. Okay, our next speaker, our final speaker in the school, is Sheng from Washington. He was a postdoc here with Nick a few years ago, so know him very well. Welcome back. In case you don't know, he discovered superconductivity in uranium telluride, so he did a lot of groundwork for us. So thank you for that. And thank you for giving the talk. Okay, so laser advance. Sure. Yeah.
Okay, just to make it clear, I didn't discover. It's a group of people, Nick and me, and you know.
I'll never forget when you brought the curve and said, "Look, I'm a superconductor."
Okay, all right. So it's great to be back. And when I was postdoc, we also had a winter school every year, and I used to run the floating zone furnace. I really enjoy doing that. Now coming back, I can no longer do that. I can only give lectures, which makes me feel I'm no longer young.
You're welcome to come back.
Next time. I mean, the workshop is mainly about the high pressure, and I'll talk about this clamp type pressure cell. And my own background is sample synthesis. When I was a PhD student, within the group, there are some students dedicated for synthesis. Some students only do high pressure. At the time, I really think, you know, high pressure is a totally different world from what I was doing. And I never thought I would do high pressure work. But now I really think, you know, all the students, we should try to expand your horizon. So I really like the idea of this workshop. All the students can get exposed to wider, you know, range of different experiments. I also tell my students, don't think as a technician. I'm specialized in sample synthesis, or I'm specialized in high pressure. I'm specializing in certain type of experiment. Think as a scientist. What is a scientific goal you want to work on? Then think about what techniques you need to achieve that goal. If that's something you already know, you work on it. If something you don't know, try to learn. Or if something that's really outside the available resource, you can try to collaborate. Or in the future, you can work on that. So this is one example. The first pressure experiment I did was a few years ago when I was working with Nick. And back then, it's really a graduate student who assembled the cell. And all I did is, over the weekend, I go there, squeeze, and put it back again. Now in my group, we started this type of cell. We're working on the diamond element cell also. We just started. And I think we don't have to be a real expert to do experiment. You just need to know enough and keep learning. So this lecture, you can think of this as a senior student sharing experience with younger student. Okay, hopefully you already know a lot about pressure. And actually the principle behind pressure is very simple, right? F over A, and even my son in 5th grade, he already knows this. That's really the principle. Sorry for this. So to do this, what you need, you have a certain area that you apply force. Right? So this is the simplest type of pressure cell. It's a piston cylinder cell, which I will focus on today. And so the two ways to increase the pressure, one, of course, is to increase the force. That's what we do in this type of piston cylinder cell. And the other one is to reduce the area. So if you really want to go higher pressure, you need a so-called envy cell. So this is a Bridgman type. Well, I forgot the name of this person. Started with D. And the other one, you can add a multi-envy cell. And you probably saw this for the furnace. Okay, so in terms of pressure study, there are this many available pressure cells. And the order is in the order of hydrostatistic. So the helium gas pressure cell, the hydrostatistic, is supposed to be the best. And the pressure you can get to somewhere around 1 GPa. The piston cylinder cell that we're going to focus on, you can get to 2-ish GPa. The reason is, here you have a gas as a pressure medium. And going here, you have a liquid, at least at room temperature. At some lower temperature, it's going to solidify. But when you apply the pressure medium is the liquid. So it's slightly worse than the gas. Then moving downward, Bridgman, at least the original Bridgman cell, used a solid as a pressure medium. And the hydrostatistic is slightly worse. And you can go to 7 GPa. Later on, people modify this type of pressure cell so that you can include the liquid as a pressure medium. And you can go to 7 GPa. And then now we have diamond envy cell. You can go to 200, above 200 GPa. So obviously, high pressure is more interesting. We just saw that you can get to almost a room temperature superconductor under 250-ish GPa. Then the question is, why would we even care about all this low pressure? In my opinion, there are multiple reasons, but mainly there are, I think, 3 reasons. One, some materials are really sensitive to the even slight pressure. This is, at the time I made the crystals. So someone else did the high pressure study. This is an iron-based superconductor. And the idea behind this is superconductivity is in the close vicinity of the magnetism. And here we have a cobalt dope. And if you don't apply pressure, it's anti-ferromagnetic state. If you apply slight pressure, you can drive this down to almost 0 and go into a superconductor state, then go into a non-magnetic so-called collapsed tetragonal phase. So if you look at the scale, this is mega power. So in terms of GPa, this is 0.2 GPa. That's really small pressure. Using a diamond envy cell for this, it's not a good idea. My more favorite example, this is uranium ditellerite. And we had the superconductor, we did a pressure study. And this is actually not my work. At the time, there are 3 groups who did the pressure study. And the reason why I put this one, on our phase diagram, the TC linearly go up. So if you look at this phase diagram, and the group, the TC actually come down first, then go up. So we did it too fast. Right? The pressure, we increased it too much. So we didn't even see the decrease of the TC at the beginning. So that's another example where sometimes you really need a low pressure, not high pressure. If you apply too much pressure, you miss this one. So that's one reason. Sometimes the phases are very sensitive to the pressure. Another reason, this type of piston cylinder cell, because we didn't reduce A, the area can be large. That means you can put a large chunk of material in there. The cell that we use, the diameter is about 5 millimeters, and it's about 2 centimeters long. That's the sample space. So we do transport study. But sometimes people are interested in, for example, neutron study. For neutron, you need giant samples. For a diamond envy cell, this is almost impossible for example, inelastic neutron study. But the piston cylinder cell can work. So this is a cell that people designed 10-ish years ago. And with no cell, you have this much neutron intensity. And with the cell, the concern is that the neutron will attenuate. But they manage, we're going to talk about this later on, they manage so that even within the pressure cell, the intensity doesn't reduce dramatically. There is attenuation, but it's okay. possible for experiment. Another one is a μXR. You also need a large crystal, and that's possible with a piston cylinder cell. Okay, and third reason is this type of cell is really easy to learn. I'm going to show how you assemble the cell. Hopefully, by end of the talk, you know how to do this. Okay, so this type of cell started about 70 years ago, 1953. This is seminal work of in the field. At the time, pay attention to this. So their work provided over 20 times higher pressure. One work is over 20 times. That's really impressive work. So what they did, they studied how the TC of superconductor change under pressure. So to appreciate this, I want to go through how people did before this, so you appreciate why this is important. The first pressure study in terms of low temperature research is actually done by Onis. So this is, at the time, this is the setup. The idea is very simple. They use helium to cool down the sample. Then if they squeeze a helium gas into the chamber, then you increase the pressure. So if you look at the setup, there are two tubes going down to the sample chamber. And the one is there will be some electrodes coming out for experiment. The other one, you can squeeze helium gas in there. So with this setup, they can reach 300 atmosphere. That's actually pretty sizable already. We have a tube furnace. There's a floating zone tube furnace that we have for this winter school. We can go probably 10 atmosphere. Yeah. So at the time, they can reach 300 atmosphere. That's pretty large already. But TC got surprised by only this much. So the next improvement, they use so-called ice bomb. The idea is, instead of using helium to squeeze the sample, what if you put water there? At a lower temperature, of course, water is going to freeze. And we know that when water freezes, the volume actually expands. So that will squeeze your sample. With this setup, you can reach a lot higher pressure. However, you only get one single point. There's only one pressure for each experiment. That's how people did. So if you look at this study again, so how do they achieve higher pressure? The clue is here. They use a technique due to bridgman. So this is already 1944. Actually, 10 years before this, Bridgman invented this so-called bridgman cell. The bridgman cell, F equals over A. The idea is to reduce A. So he uses envy cell. Reduce the area, then increase the pressure. And he can get to 40 GPa. The issue is, this setup is only supposed to be used at room temperature. So you have a giant machine to squeeze the sample, to apply the pressure, and they measure resistivity at the room temperature. So you can see electrodes are on the envy cell. So you put sample here, contacts on the other side, then you measure directly from there. So this is a giant machine. And also at the time, this type of cell does not use pressure medium. So the hydrostaticity is not good, but he assumed the pressure is actually uniform. Okay, so 1953, the question is, can we use this type of cell, go down to lower temperature? Right? Think about your cryostat. You only have this much volume in there. Obviously, you can't put a press there. So how do we keep that pressure secured after you release the external force? That's a key question. So here's a design. That's why it's called clamp cell. The design is actually simple. Use a screw to basically use the friction. So here's the Bridgman envy cell. You still squeeze the cell at room temperature. Once you squeeze, then you use a screw to screw it down. and lock the pressure. It's only that simple. But this is a really important progress in the field. It took almost 20 years between the Bridgman cell and the low temperature Bridgman cell. Okay, so at the time, the first clamp cell actually is a clamp cell Bridgman cell. It's not the piston cylinder cell. So let's talk about this Bridgman cell a little bit. The next advance is to increase the hydrostaticity. Anyway, the idea is you need pressure medium. You do not directly squeeze your sample. You want some medium. So the idea is you use a so-called gasket. So with this gasket, so now there's some enclosed space where you can add your pressure medium and it will hold there. So at the time, most of the gasket, you use this pyrophyllite. It's a mineral. And the pressure medium is this steelite. Both are mineral. And for this, of course, let's say you measure resistance. You need some electric contacts coming from your sample, go out of the gasket. So now you can't directly go to your cell. You have to go out of the gasket. So you drill some hole so that it can come out. Because of this, you cannot use liquid. You have to use some solid, otherwise the liquid is going to flow out of the hole. So people have been thinking, can we include a liquid medium? So at the time, there are a few other papers also. This is from Grenoble. And the idea is you use 2 layers of gasket. The outer layer is still this pyrophyllite. And inside this gasket, you use this nylon. And nylon is soft. Once you squeeze, you cut some hole, and the electron leads come out of this hole. Once you squeeze, the hole will get closed. And if you have liquid there, liquid will stay. With this type of thing, you can still get to 7 GPa. That's a Bridgman cell. What I want to focus more is the piston cylinder cell. So still in the clamp cell, instead of Envy cell, you can just put a piston. So here is a sample space. Maybe this is a better picture. Here is your sample space. Typically, it's some Teflon capsule. I'm going to show you later. And then on one side you hold it from the bottom, and this is where your sample is, and your electrodes come out. This is so-called feed-through. On the other side, you have a piston, which is typically tungsten carbide, and you squeeze, then you lock it. Okay. There's some details to improve this that came later on. One is the so-called mushroom type of seal. The idea is once you release the force, how can we minimize the loss of pressure? Here they use this piston looks like a mushroom. The idea is this is what you push the piston. Between this one, you have 3 layers of washer. You have beryllium copper, then a nylon, and a beryllium copper. Then you push on this side, and here you have unsupported area. When you push this side, the nylon, because it's soft, it's going to expand. Instead of you push this way, it's going to expand this way. Once it expands, you basically increase the friction between the washer and the wall. So you kind of enclose it, and the pressure will stay there. Another thing is so-called anti-extrusion ring. So we have this Teflon capsule. If you squeeze too much, the Teflon is very soft. You have a risk of squeeze it into the space between the piston and the cylinder. So people invented this anti-extrusion ring. Basically, it's a metal ring, so that it will not go into this space. Another important detail is this feed-through. Most of the time, is the piston cylinder fail is because of this feed-through. So you have your sample here, and you have to have some electrodes coming out. So how do you make sure there's no leak? So we use some die-cast, and this cone shape is very important. Most time it fails is because of this. Okay. Here are a list of materials that you can use to build this piston cylinder cell. I'll mention a few. The most famous is tungsten carbide. It's very hard. So very good for high pressure, but also very hard to machine. And it's somewhat magnetic. If you have extremely pure tungsten carbide, it will not be magnetic. But you don't get that. The industry tungsten carbide typically is mixed with some cobalt or some iron, and so it's slightly magnetic. If you don't want this, you can use beryllium copper, which is also very good. However, so typically you have 2% of beryllium in there. The machine shop will not like this. At least our machine shop refused to work on this. But it has very low sustainability. Somewhere here you have a nickel chromium aluminum. I asked ChatGPT why you use this instead of beryllium copper, and it didn't give me a very good reason. Eventually, I found a Japanese paper, but it's all in Japanese. Then ChatGPT translated it for me. So I finally figured out this one at room temperature is not as good as beryllium copper. However, at very low temperature, it has a very good strength and stability at very low temperature, according to that Japanese paper, which I cannot understand. And in terms of magnetic, this one, there's nothing magnetic. This one, it might be slightly magnetic, but better than this. So, in the literature, you will see a lot of cells that are a combination of many of these materials. That's because now people typically use 2 layers of cell. One layer is for one purpose, the other layer is for another purpose. For example, here, in this design, or this is from the Japanese paper, actually later on, I think they started the company. So the inner cell uses nickel chromium aluminum. The strength is not as good as beryllium copper at least at higher temperature. So they have another layer of cell with beryllium copper. Okay. This is the type of cell that we use. It doesn't have that mushroom cell, but it works pretty well. So it's from this company, and you can see the cell. We have 2 layers. The outside is beryllium copper. Inside, the color is different. It's this nickel chromium aluminum. And then you have this. Here's your piston. That's tungsten carbide. Then this is that anti-excursion ring, and this is your Teflon tube for the sample space. And here's your feed through. And this is the bottom one. There's a hole the wire can go through. Okay. This cell you can put in dilution fridge, or you can put in even PPMS and PMS. The size fits well, and you just need an adapter. If you want to do a PPMS measurement, you need an adapter to go in there. Okay. So in next few minutes, I'm gonna go through the procedure. So hopefully you know how to use it. You can go to this company. The sale is about $7,000. You can get one, and here's the introduction of how to use this. So you start with this bottom screw, and this is tungsten carbide going into this. There's also a hole. To start, you want your copper wire go through this. Depends on what type of measurement you want. If you want just measure resistance, you need basically 6 or 8 wires, because you also need the pressure gauge. If you want to do a Hall measurement at the same time, you can put 10, 12 wires. The size of the hole is enough for put like 12 or 16 wires. Okay, so you have wires go through this one, and this is a plug, and this is the one that we use for the feed through. Okay, so as wire goes through this, then you make a feed through here. Okay, we didn't show how you make a feed through, but basically you use a die cast to make sure it fills the inner space of that plug and make a cone shape on the top. On the other side, this wire goes into some pinheads, and it's important to label which one is which. Okay, then this is a feed through. You have some cone shape here, and these are those 12, 16 wires, and some of this will be used for the measurement, your sample, some will be the pressure gauge. Here, this is not from us. Our picture is not as nice as this. So here you can put your sample here. Yeah, picture here. You put your sample here, your wires go to those copper wire. And on the other side of this, you put two pressure gauge. One is for the low pressure, one is for the low temperature, one is for the high temperature. We'll talk about that in a second. Okay? So now you have this feed through, right? So then that feed through, together with your sample, go into this Teflon capsule. And the capsule is filled with liquid. And we'll touch on that liquid. There are wide variety of liquid you can use for this. Okay. Again, this is your feed through. You plug into this capsule. Then you take the whole thing, you put into your cell. Okay? For this, you just squeeze. The other side is hollow. There's nothing yet. You use your hand, push it down so that it's flat here. Then you can screw this one, that tungsten carbide is already in there. Then you can screw it to the bottom. Okay. So one side is finished. Then we need to flip. As you flip, because you have wires coming out, we're gonna eventually squeeze this, so you want something to support without breaking your wire. This also comes together with from the company. Then you flip, so this is the other side. You can still see that Teflon capsule there. Okay. Yeah, that's a Teflon capsule. And on this side, you put your piston there, and this is a backing plate, which you directly push on. You don't directly push on the piston. Okay, so you put your piston there, this backing plate, together with that screw, you put it on there, then it's ready to squeeze. Okay, you take it to a press, you squeeze this, then you just tighten the nut. That's it. It's only that simple. The part that is difficult is the feed through. It might take some practice and some time to make the feed through and put your sample on. Once that is ready, to assemble the cell really takes 2-ish hours. Do it carefully. That's it. Okay. So let's talk about some details. One is a pressure medium. So what kind of medium you want to use? You don't want to use water. So what people use, there are a wide range of oil that you can use. And this is, I didn't put the citation here. This is a paper from my PhD group. So they studied which medium will solidify at what pressure. The idea is, at least at room temperature, you want this to be liquid. Right? So when you apply the pressure, it can be uniform. So if you just look at this graph, seems like this one, the 1-to-1 ratio isopenting N-penting seems to be the best. Seems to have a wide range, larger range of pressure range where it solidifies. In reality, for example, for the piston cylinder cell, we actually prefer this Defin 7373. This is a minor oil from some organic oil from Japan, and it has a smaller range of pressure range. But for piston cylinder cell, this is enough. And turns out, this one, the pressure doesn't change much as you cool down the temperature, which is also important. this graph doesn't tell you the change of the pressure. It only tells you in what pressure range it solidifies. But for example, if you do a Bridgman cell, you probably want to use one of this. Okay, talking about the change of the pressure. So this is a study from Los Alamos. It's already 40 years ago. So they use 1-to-1 N-penting iso some alcohol. That's about this pressure medium. And they studied the change of the pressure, how it changes. So there's a linear relation that they find. So the pressure does decrease in this type of pressure cell. Diamond amide cell is opposite. Diamond amide cell, typically the pressure will increase as you cool down the temperature. So you have to keep that in mind. Now, since we know the pressure will change, you better know the pressure. You better know the exact pressure. The way how we know the pressure, we put typically two pressure gauge. One is this magnetic wire. This works well for room temperature. So basically, the resistivity will change as a function of pressure. And if you calculate this, the change is actually pretty sizable. But this doesn't work well for the low temperature. For the low temperature, we typically put a superconducting sample and measure TC. And all those conventional superconductors, they have a well-defined TC dependence. So typically you can put a lead, sometimes the tin. The important thing is you want to make a really the normal state resistance. The metals are really metallic. The normal state resistance can be very, very small. So what you want to do, you want to make a really long and thin wire. And sometimes you even use a hammer to abuse it and try to increase TC, normal state resistance, but hopefully TC will not change. And another thing is, for this type of superconductor, the HC is typically very small. So if you have a remnant field, that can change your reading of the pressure cell. So typically, you also want to scan your field from negative to positive and really find where your zero field is and read the.
How was calibration of these done originally? I understand you use it as a gauge now, but you didn't know how did they know how did they calibrate this TC versus volume?
That's a good question. On the pressure, the honest one, I look at that literature. The other one, this one I didn't look at in detail. The one in honest paper, the temperature is read from the gas, the vapor pressure, and that's how you read that verifying temperature.
This is TC versus
pressure.
Volume or pressure, right?
Versus pressure, yeah.
So that's what you need to know is the pressure.
Yeah, the pressure. Yeah, that's a good question. How do they originally read? Yeah.
Speaking was Ruby for Ruby.
Yeah. Ruby. Okay.
And Ruby was Bentley. Yeah. Eventually, you need to know something.
Yeah, you need some. Yeah. That's another way to from the Ruby you can read the pressure. That's something we didn't include here. Okay. All right. So up to this point, hopefully we know how to use a pressure cell and do resistance measurement. But this type of cell is actually very versatile. You can do, for example, magnetization measurement, and you can put in a PPMS, NPMS for squid measurement. And there, the sample chamber is very small, so the idea is you only use one layer of cell, and so the pressure cannot go very high, 1 GPa. You can do specific heat, and in this case, people do AC specific heat.
Just to say, that's the same company you mentioned.
Oh, the same company.
Makes that cell.
Okay. All right. Well, I didn't know that. Yeah, I'll probably buy one. So the DC is hard to measure because you have all of other liquid, all those. It's hard to get absolute value, but you can do AC specific heat. For details, you can refer to this paper. Basically, you put a heater there, you have thermometers, Yeah, and you apply an AC current to the heater and detects the change in the thermometer. So here's the setup. You can see the sample on the heater and the thermometer. As I mentioned, one advantage of this type of cell is for the large volume, large sample volume. So this is their design for the neutron scattering. The idea is the neutron, when it goes through either beryllium, copper, or other material, the neutron will attenuate. So what they did, first they used two layers of cell to maintain the high pressure, but also where the sample is, they make this neck type of thing, so that to reduce the attenuation of the neutron. And again, they can achieve, this is only like 1/4 of attenuation. Another thing you can do is mu-SR. So here, the key thing is to choose the right material. Some material, the muon will relax more in some material and less in other material. So they tried different materials, and turns out this MP335N, the combination of this and the beryllium copper is the best. Do I have a picture there? Okay, I didn't show the picture there. But with this type of cell, you can go to 2.2 GPa, and with not significant relaxation of the muon in the pressure cell. All right, I still have a few minutes. So since I'm the last talk of the workshop, I think there's one more thing that is not covered in the workshop, but also very important. So here, in all this pressure cell, the key point is you want a hydrostatic pressure. However, sometimes uniaxial pressure can also be important. So in the next few minutes, I'll briefly go through how you can do this. So the uniaxial strain, when you apply a strain to the sample will respond not only in that direction, but also in the other direction. So the stress is actually a tensor. In some sense, this is like a magnetic field versus magnetic moment. So you can get more information in some sense out of this type of experiment. So one of the early on example is the iron-based superconductor. At higher temperature, its structure is tetragonal, and in lower temperature, it turns into an orthorhombic structure. So A and B are no longer the same. However, if you just measure the sample, you don't see any anisotropy, because when it transforms, it has domains. So here you can see sometime in some region A is here, in some other region A is here. So in average, if you measure anisotropy, you don't see any. So this is how people want to use strain to detrain the sample. This is from about 15 years ago. This is from where I did my PhD, another group. So what they did, they really used a mechanical way to apply the strain. So here you have some metal, and you have a screw. You screw it in, or screw it out, you apply a strain on the sample. And with this very simple setup, they can really achieve almost fully detrain the sample. And this is another similar idea. They use a cantilever, but also in some sort of mechanical way to apply the strain. And by doing this, people can indeed detect the anisotropy of the sample. And this was 15 years ago, and just by doing this, that's a science fiction. That's the power of the idea. So now people have better way to apply the strain. Now they have used this piezo stack. And so you have, in this case, you have 3 stacks piezo. These two are connected to one. So if the piezo material, when you apply a voltage, it will expand or shrink. So there's this stack and this stack. One stack, when you apply positive the voltage, it will stretch. The other direction, if you apply positive voltage, it will shrink. And so you have the flexibility. And the idea is, if you only have one stack, the material itself will have thermal expansion. This will have some thermal expansion that already applies some strain to your sample. But if you have two stack connected to two sides of the sample, the thermal expansion will get canceled. So that's the idea. After this paper, they also started a company. Now you can get this cell easily from the company. And these cells are even easier to use. You can do all kinds of experiment. For example, this is our picture. In this case, we do resistance and the AC magnetization at the same time. So basically, you have a sample here. It's hard to see. You glue to two sides of this, and on one side we put 4 wires for resistance measurement. On top of this, the company sell us this AC coil. One coil is $100, but I think it's worth doing this. You put this coil, and if it's a superconductor, you can see zero resistance and the Meston effect at the same time. It's very nice. And people can also do a thermodynamic measurement. This is AC elastical caloric effect. The idea is you put a thermocouple here. In our case, we apply a DC voltage to the sample. In their case, they put a DC voltage to the sample. On top of that, they put a tiny AC voltage to the sample. And that AC voltage, basically is you're going to drive the sample like this. And that will release heat. So then you can detect the change in thermometer. So that's going to be a thermodynamic measurement. And from there, you can see a thermodynamic signature of condition. This is strontium leucine. All right, that's all I have, and I'm only 1 minute over. If you have questions, we can discuss.
Okay.
So I have a question. So I haven't really used any of these detection strain devices. How do you account for how much the glue or epoxy itself is being compressing or whatever? And does that affect how much strain or stress you actually put in? Is the strain and stress some quantifiable value? And then you have to somehow take into account how much the glue itself is compressing to calculate the actual strain that you're putting on the sample.
You mean how much, for example, die-cast we put on this side?
Yeah.
Yeah, that, our experience, you always want as strong as possible. And typically, when this type of experiment fails, is where this fails. Typically, the sample will not break before this breaks. So our experience, we want to make this as strong as possible. As to this, how much is too much to affect the strain you put, I don't know.
This is an art form.
Yeah, exactly.
You also asked about how do you measure the strain.
Yeah. How do you quantify how much strain you put?
Okay. So at the same time, you have there's a capacitance measurement. You go at the same time, so you know the distance, the change of distance.
Or you can put a strain gauge on the sample directly. Question.
So it's pretty related, but I was just wondering, can you give some sort of idea of scale of the amount of strain you're able to put on a sample with this type of device?
It varies from sample to sample. People also do 2D materials. There you can put pretty much.
In strontium ruthenate, they got up to above 1%, which is
Here you can see.
which is probably the maximum.
Yeah, on this one, this is about close to 1%.
But in typical materials, you won't get that high.
And then trying to rotate 214.
214. Which turns out to just, you can strain that material quite a lot. But most materials you cannot for that high. Yeah.
Do you also perform magnetic measurement of the cell, or just
A magnetic measurement in which one? The piston cylinder cell.
you use
piston cylinder cell, we try to put once we got this coil, we try to put that coil in the piston cylinder cell, and that can work.
So, you said for the single lane cell, right? And also reduce the maximum pressure how much pressure that?
Yeah, that one, because it's single cell, you can only go to 1 GPa.
1 GPa. And sorry, last question. Look like most material you use for the cells, they kind of more or less magnetic. So when you use that for the magnetic measurement, how you kind of calibrate the background?
Yeah, I think Valentine has more experience on this. I remember when he does this, you have to first measure the background of the cell, and then you put the sample in, you measure it again. Is that right? I've never done this type of MPMS measurement, but that's my understanding.
Yeah, the clamp cell you showed is too big, right? So
No, the MPMS cell.
the MPMS cell then it has to be non-magnetic, and you have to go often you have a background no matter what. To measure that background before with like no sample inside.
It's the pressure is lower here also because you want to have a reasonable sample space. You could make that smaller, you could probably get a higher pressure, but then your signal goes down.
Yeah, so eventually you can only measure field magnets instead of fine flux.
So the other way, just for completeness, we do this with the mag lab, for instance. You can do what's called the TDO experiment. Essentially, wrap the sample in some coil, and rather than just try to measure some kind of cytometry, you use the TDO technique, which measures the change in inductance very sensitively. And you can do this in a pressure cell, and so on. Up here, and then
Did you say that if you don't use pressure medium, we can see like apply the pressure as the strain, the tensile strain, stress, and then can we see like a quantitative value of like this, the stress applied to your sample with pressure?
So actually, in the original Bridgman setup, there is no pressure medium, and it's assumed that the pressure is uniform. The idea is, in the vicinity of at the top layer, the sample might go into some very soft shape, and that will redistribute. So even though you apply uniaxial, if it redistribute inside the sample, and also when you apply pressure like this way, there's some force along this direction that will apply the pressure inside of your sample. So the assumption is, even though you apply pressure like this, you still have a more or less uniform pressure.
There is no way you can know how much.
I think with some analytic tool, you can probably, nowadays, for example, this use some finite element analysis, you can probably simulate the force inside.
I have a two-part question. I assume that virtual versions of both console as well as devices are that they easily fit within the volume restrictions like a gas versus illusion fringe. How easily can either of these devices be adapted to like angle resolve measurements, where now volume is restricted by the rotator you're using?
Rotate.
So you can make a very small distance on yourself, but where your thumb down, and you'll see it right there.
The ceiling on pressure goes. What's the maximum pressure that
About 2
GPA? 2 GPA.
Yeah, and if you want to take it to failure, you can set up the box with no high and low.
so similar pressure is this is only 2 It's a 2.2 GBA.
That's 2.2 GPL. Yeah, and it's single wall. We don't use it as a multiple wall. But it's, we have one that's about 8 wall and another one that's 8 wall.
The other way is to just put that in a vector mag.
There you go.
And just a quick question, would these smaller versions be commercially available, or are they all things that you need to get first edition?
Yeah, but we haven't commercial. Are you asking whether it's commercial? Right. Yeah, we've not commercialized them. They have to use the dark. They're trickier than the cells with approvals. They're essentially called that. The monitor machinist is top notch and we use either Google or aluminum or anything. Just have to have a lot of patience.
Any final questions? Okay. All right, thank you, Sheng. Okay, so as I said, we're going to have a very short break so that we can get to the discussion. So I'm going to give you 10 minutes to get some coffee, use the restroom, and collect your prize. Yeah. That was the fun part. Yeah.
So is this an American or European?
No, no, it's a European market.
Oh, don't worry.
You're that.